Okay, hello everyone. Today we have Ignacio Trujillo here to talk about the stellar halos, and this is a breaking news talk. So you probably all know him, but he did his PhD here at the IIC, working on galaxy morphology and size evolution, and then he did his first postdoc in Heidelberg at the MPIA, then moved to the University of Nottingham before coming back here for a Ramon y Cajal fellowship, and now as an entitled researcher. And yeah, welcome for this talk.
Okay. So can you hear me? It's fine? No? Should be on, no? Okay. Okay, so thank you for coming, and also I would like to greet the people that is listening by the stream too. So today I'm going to talk about a paper that it has been recently published in Molly Notices, which I did with Judith Bacos in collaboration with her. And it's a paper about the stellar halos in galaxies, but not in the nearby universe, but very far away at redshift 1. So how this component of the galaxies were 8 billion years ago. So when you talk about the stellar halos, you should notice that the stellar halos are an extremely faint component of the galaxy, the most subtle component of the galaxy. So it's around 1,000 times fainter than the darkest sky that you can find in the Earth. So it's extremely difficult to observe even in the nearby universe. Because it's so faint, it also contains only a few % of the total amount of stars of the galaxy. So it's a prediction from the cosmology that is in all the galaxies, but its contribution to the total amount of stars is just 2-3%. So you really need to explore this component of the galaxy to go extremely deep. So here on the left is an example of the nearby universe. Observe it's a galaxy which is relatively nearby, so a few dozen of megaparsecs. It's 7716. And this is the image that you have of this galaxy when you observe through a regular survey like a Sloan. So your eyes are able to see 25 magnitudes per square second here. This is the limit that the image shows. So you really need to integrate another 2 magnitudes to start seeing that the galaxy grows quite a lot, and it has a lot of stars. Few % of the stars, but very extended around the objects. So why stellar halos are so relevant when they contribute to the total amount of stars so few? So they have even less stars than the smallest values in the universe. Well, the reason is related to the morphology, to the cosmology and how the galaxy forms. So it's a natural prediction from the cosmological model that all the galaxies universally have an stellar halo surrounding the object. So this is a model from Cooper et al. 2010 simulating Milky Way galaxies. And you can see that in all the realizations, when you go very deep, so this is 30 magnitudes per square second, you find extremely extended stellar halos surrounding the galaxy. So this is connected to the morphology because the stellar halos appears as a product of the continuous infall of satellites, okay? So if you change the morphology, you change the stellar halo. If, for example, if you change from cold dark matter to warm dark matter, you basically have very few satellites to form the stellar halo. So you would expect that if you go very deep, you would find very little stars there, or even no signatures of a stellar halo at very low super brightness features. So it's well connected to how the galaxy is assembled, and for that reason, also because it has a lot of, it takes a lot of time to evolve and change because they are huge structure. They are a very nice fossil record of the emerging activity of the galaxies. So that's the reason why studying stellar halos is so relevant. But also, you can ask, and why do you go to redshift 1? I mean, it's so difficult to find it even at low redshift. Why do you need to go to redshift 1? Again, this is connected to how we understand the galaxy forms. This is, again, from the same paper, and you can see here the infall redshift to the halo of the satellites that have formed the halo, and this is the mass of the satellites that has infall. Here, for your comparison, you have the typical satellites of the Milky Way, so you can have an idea of the typical mass of these satellites. So you can see that the largest contribution to the stellar mass in the halos is produced between redshift 3 to 1 or so. So you can see that, okay, you have a lot of a small infall of satellites here, but it is here when you have satellites with enough mass to modify and to create substantially the stellar halo of those galaxies. So it was only in one case where they found one satellite infalling after redshift 1. So the prediction from the cosmological formation of the galaxy is clear. So most of the assembly of the stellar halo is around redshift 1 to 2. And after that, in the last 8 billion years, you expect very little infall of satellites, I mean, with enough mass to form the substantial part of the stellar halo. This is for a Milky Way-like galaxy, okay? Yes, we are talking about these galaxies of the mass of the Milky Way. So since redshift 1, the prediction is that basically the stellar halo should evolve passively, and then basically nothing has changed too much. So that's why we decided to explore this frontier of redshift 1. Of course, there are many different techniques to explore the stellar halo, but all are based on going extremely deep. By extremely deep, we mean exposure of, with our current telescope, of dozens and dozens of hours. When the galaxy is relatively nearby, so they are from the local group, you can resolve the stars. And because you can resolve individual stars with a deep observation, but relative modest one, you can detect the stars and go so faint up to 32 magnitudes per square second. The problem is that you are limited by the resolution of your telescope, and that allows you to explore so deep the galaxies up to 5 megaparsecs or so. You can integrate photometry and then expose your galaxies quite a lot, and you typically reach with current telescope and with normal amount of time that you allocate to these galaxies, in the limiting case around 30 magnitudes per square second. And the problem that you have is that because you don't resolve the stellar populations, you have to explore these objects using broadband photometries. These are well beyond the possibilities of any spectroscopic analysis because they are extremely faint. So this has limited the stellar halos study so far to the local group, where you have seen very wonderful images from the group of Annette Ferguson, Irwin, and collaborators of the Milky Way, our own Milky Way, M31, M33. In the nearby universe, we have been able so far to go up to 100 megaparsecs and explore the stellar halos up to 28, 29 magnitudes per square second. And the farthest away analysis that has been taken before this paper were up to redshift 0.3 from Civetti and Ferguson. But they're still far away of this frontier of redshift 1, which is what you would like to explore, to test the cosmological model. But of course, observing stellar halos at redshift 0 is extremely demanding. Observing at redshift 1 is like it's crazy. That's why nobody tried before. And the reasons are clear. It's a very faint galaxy component, and in addition, you expect, because you are at redshift 1, a cosmological dimming of 3 magnitudes. So you can imagine how deep you have to integrate to obtain, to observe the stellar halos at those redshifts. So that was the reason why nobody tried. So, but we tried because we thought that, okay, what happens if we take the Hubble Ultra Deep Field, which is the deepest ever imaging of the universe, and we take advantage not only of the optical bands of the ACS camera, but also of the near-infrared camera. Because as you know, if you go to the near-infrared, you are detecting more light also, because the populations are brighter there. And we tried. So the first thing we did was in the Hubble Ultra Deep Field, which is a relative modest field of 4 by 4 arc minutes, we selected 2 spiral galaxies which were at redshift 1. And this is how they look like. So these 2 galaxies are, this is a redshift 1, and this is also because of the selection, and we selected that visually they appear like regular these galaxies. It's not straightforward to obtain, to select these galaxies at those redshift, because at those redshift, most of the galaxies that you find are already forming, interacting, and so on. So finding a couple of galaxies that looks relative well-behaved or quiet is complicated. So, but we selected two galaxies that resemble Milky Way objects, and also they were selected not only because of the redshift, but also because of the stellar mass, which is of around 3 times 10 to the 10 solar masses. So it's just a little bit smaller in mass than the Milky Way, which is around 6-7 times. So this would be, in principle, good progenitors of the Milky Way in the today universe. So this is how they look in the B-band rest frame, in the Z band, so it's the B-band rest frame, and this is how they look in the I-band rest frame. So this corresponds to H-band data. Unfortunately, and you note here a difference between the resolution of these two, so we were only able to explore with the Wide-Field Camera 3, the better data, only one of the two galaxies, because the other one was outside of the field of view, and we have to base our analysis on the NICMOS data, which is a little bit worse. So what happened when you explore the surface brightness of these galaxies? Well, the first thing is that you note, so this is arc seconds, this is the radial distance, and this is the surface brightness that you observe, the surface brightness profile in all the bands that we have available. So the most remarkable thing that you find is that these two galaxies have an inner region up to 8-10 kiloparsec, which is relatively flat and decaying, and then you have a very sharp break going down very quickly. And then at the very end, at around 16, 17, or 20 kiloparsec, the slope changes again, and you have an excess of brightness compared to what you expect from the decay of light here. Okay? So the most remarkable thing is not only that it appears in the two galaxies, which is nice, but also it is in all the bands, not only in the optical bands, but also in the near-infrared bands. So it looks like there is something real going on beyond 15 kiloparsec in the two galaxies. Of course, here you can see that for the NICMOS data is extremely noisy. So most of my discussion will be related to this stellar, well, what I think is a stellar halo here. Okay, so for you to have an idea of how far we are exploring this galaxy, also how good the images are. So here it's the galaxy again, but this time I have combined all the different near-infrared bands, and I have filtered the image to highlight the very low surface brightness feature. So here is the position of the break that I mentioned before, when the slope of the galaxy changes quickly and goes down, which is at 8 kiloparsecs. This is the transition region from 8 to 15 kiloparsecs, where the surface brightness decays very quickly, which I think is the outer disk. And then we are obtaining the surface brightness here. Of course, you see that the galaxy, it's surrounded by other galaxies that could be satellite or background or foreground satellite or galaxies. So what we did was to mask very aggressively all these regions to avoid the contamination of any light surrounding the galaxy that was clearly connected to other objects. So we are basically, what it follows is basically the exploration of features of this kind, okay? So the light that is surrounding this, but when you mask all this region. So, the first thing to explore, and this is the most technical part of the talk, but I think it's very interesting because it's a new regime of exploration, so you really need to understand the problems with the instrumentation. See. Yes. No, I mean, in fact, for the near future, so we have selected two galaxies to make a pilot survey. But for the near future, we can use up to maybe 20 galaxies or so. There's something like that at different redshift, and if you are more flexible with the morphologies, for example. Okay, so this is a pilot program. So now let's go to the difficulties in terms of technicalities. So the first thing that you have to notice is that the objects are very small. So we are talking about objects of 1-2 arcseconds. And we are exploring a region which is very faint. So here, the PSF could have an effect. You normally have heard that the PSF is basically affecting the central part of the galaxy, smoothing the profiles and so on. But here, again, I mean, we are going so deep, we are reaching 10 to 12 magnitudes per square second in range, that if the PSF has tails, you can spread light from the center to the outer region, forming maybe an artificial halo, okay? So that's why we study this in detail. So these are the PSF of the ACS data for the Z band, and this is the PSF shape for the H band data, for the 160. So you see how relevant are the wings of this PSF when you go so deep. So you see that you spread light of the PSF up to distance for the near infrared band, even up to 2 arcseconds or so. So the first thing that we did was to explore whether the PSF affects to the shape of the profiles. And we found that this was the case. So here, this is the SUFA brightness profiles observed. And this is a model of the galaxy that modeled the bulge, the inner disk, and the outer disk. What happens if you convolve this model with the PSF? If you do that, this is how the PSF affects this red model here. Okay? So you see that there's quite a significant amount of light that appears by the effect of the PSF in the outer region. Still, if you model the inner region and you convolve with the PSF, you are unable to reproduce the full brightness of the outer region. But you see that the significant, so you should take it into account when you explore the properties of this excess of light here. So taking into account that, what we did was the following. So we model the galaxy with the bulge, an inner disk with the truncation here, and something like an stellar halo component here. If you do that, you produce this red line here, okay? And when you convolve this model with the PSF, this transforms into this line that goes through the points, okay? But look at this. If you didn't take into account the PSF effect, the real SUFA brightness of the stellar halo in this region would be wrong by an order of 1 magnitude, okay? So you can see that the effect of putting light out there is quite significant. So on what followed, we did this for all the bands. And here, what we did was, okay, so this is the data points, this is our model, and this is how the galaxy, the real SUFA brightness should look like if you deconvolve by the effect of the PSF. What we did in addition, because we are using the observed res frame, I mean, you can take your observational data and transform to res frame in slow and band, for example, R, G, and U. This is what is shown here. And in addition to, we also remove the effect of the cosmological dimming. So we transform by interpolation our data into res frame, slow and bands, R, G, and U, and also we remove the cosmological dimming to have an idea of how the SUFA brightness really likes of this galaxy. And this is what you have. So these are the SUFA brightness profiles. Now see that the typical SUFA brightness that observationally were around 30 magnitudes per square arcsecond, when you remove the cosmological dimming, it reached 27, of course, because you have increased the brightness by 3 magnitudes again. So you have removed this effect of the cosmological dimming. And here, you have the effect of the PSF in the color profiles, in the GR color and in the U minus G res frame. So this is the model that fits the observational data, and this is the effect in the outer regions when you remove the PSF contribution. So if you don't mind, we wait to the end. Okay? Yes. Okay, so you can see the important thing is that the effect of the PSF in the outer region would be, in the colors, would be of the order of 0.1, 0.2 magnitudes in the worst cases. So now we have everything. We have the SUFA brightness in the res frame. we have also the color correction. So the only thing that is missing still is a measurement of the contribution of the amount of stars in the stellar halos to the total number of stars. So these are, again, the profiles in the red frame R band. This is the observed data, and this is the correction after the PSF, taking into account the PSF. What we did was then to fit the corrected profile with the disk plus an stellar halo and measure the amount of stars that is here. So we have everything now to put our galaxies into context. And I'm almost finishing now. So this is the stellar halo light fraction that is contained in this excess of light in the outer region. This is for the nearby universe, for example, of galaxies from Judith's sample, at redshift 0, the blue points. And this is relative, these are very well-known stellar halo from M31, the Milky Way, NGC 2403, M33. And you see that quite independently of the stellar mass of the galaxy, the contribution of the stellar halo to the total light of the galaxy is of the order of 3% and so on. But the most interesting thing is that also a high redshift is the same. So the contribution of the stellar halo at redshift 1 it's, to the total light of the galaxy is very similar to today. So what happened with the evolution of the population? So here is the color, and here is the mean super brightness. Again, this is for our high redshift galaxies, and this is for the nearby sample. So the most important thing that you see here is that the today stellar halos are more redder than what you find at high redshift. And also, they are more faint than what you find at high redshift. So the thing that you need to explore now is whether you are able to connect these two regimes, these two stellar halos, by simply a passive evolution, for example. And what you find is that this is the case. So this is from Vazdeki's models for two different IMF. And these are the tracks of the stellar of a single stellar population, of a passive evolution, for different metallicities and for different ages. These are for objects which have ages below 1 billion years, and these are for populations which have of the order of 8 to 10 billion years. So the amount of time that you expect it has happened between redshift 1 to now is 8 billion years. So you can see that the stellar halos at high redshift, at redshift 1, follows very nicely the evolution that you expect if you go back in time 8 billion years. So summarizing, you have something which is brighter. This is just simply explained because of the stellar population evolution back in time. The color is bluer. Again, it's easily to explain because of the evolution of the stellar populations passively. And also the contribution of light to the total light of the galaxy is similar. So due to this reason, we conclude the following. So the stellar halos that you see at high redshift, at least for these two galaxies, are compatible with the idea of that they form at those redshift, and since then they have simply passively evolving to the today universe. So with these two galaxies, at least, I mean, this is something to explore in more galaxies, so the data is there and it can be used. We have shown that it's possible to do it. The model of formation, it's compatible with what you expect from the simulation. Thank you.
Okay, thank you very much. Now we have some time for questions. And just, I'm sorry to cut the questions in between, but they won't be transmitted with the streaming if you don't use the microphone. That's the only thing. Thanks.
Okay. Well, apologies for interrupting, but sometimes the questions have to be made right in the moment, not afterwards, right? Which is not the case now. I think I can make the question now. First of all, fantastic work. And the PSF, you assume it to be axisymmetric?
We took the real PSF, so we took the stars. So we took a bright star but non-saturated one, which are in the field, and we create our bidimensional models and we convolve with the real PSF.
So you are not assuming that they are axisymmetric. You are really
they are
taking
the real
into account.
ones.
Okay. So the point is that if you have some contamination left, you have been explaining us how careful you have been. But if there is some contamination left, you expect things like that the amount of scattered light remains. I mean, if it is contamination, remains the same, no matter whether it's high or low redshift. And you also expect that the colors change as you expect, because the contamination will be bluer. Of course, I'm not saying that that's the case, but it's just so. The second question is about these halos not varying with time. So is this to be expected? You're saying that you have one satellite and it's there for the last 8 giga-years, moving around the galaxy. Is that what you expect from theory?
As I said at the beginning of the talk, if you go back to the model predictions, so this is an example of cosmological models, state-of-the-art simulations, where they have put the stars and and they have explored. So this is for you to have an idea. So this is the typical disk. So this is the Milky Way, for example, no? Up to 10 kilo. This is huge kiloparsec. No? So this is 100 kiloparsec. So all this is the surrounding material. Okay. So they have followed this evolution of these stellar halos back in time, and they have explored when the infall of satellites happened. Okay. And when they do that, they found what I said before. So this is the infall of the satellites as a function of the mass of the satellite. So that you see that if a stellar halo today have, for a Milky Way galaxy, typically of the order of 10 to the 9 solar masses. So you can see that these are different models. The colors are different models. These are different satellites and so on. So you can see that basically it was before Redshift 1 that you formed the stellar halos, the one that you see today. So we were exploring whether this is compatible. Imagine that the simulation said that the formation was at redshift 0.5, for example, the main formation of satellites and so on. So then you would expect much more brighter stellar halos at high redshift. It wasn't the case. So they had the brightness and they contribute to the galaxy compatibly with the idea that they have just simply evolved passively since today. That's the point.
Thank you.
Okay, so I think you are convinced, and you have convinced us that the halo is somehow frozen from this set equal 1 till today.
Yes.
But could you comment about the other components in the galaxies that you are comparing with, and in particular about the length scales? Because, I mean, how extended is this halo, you have said, how big is it compared with the one we have in the Milky Way? And what happens, for instance, with the disk component that you are also modeling with your protocol?
Yes. So let's go to the disk, which I know much better. So, for example, interesting things. As I said before, one of the most remarkable things is this break at around 8 kiloparsec or so. Okay. This is the studies that we have been doing for years of exploring how the truncation of the galaxy is changing with time. So, in general, for this population of galaxies at redshift 1, what we observe is that these just increase by 30% or so with time. Okay, so for galaxies of the same mass. So if you compare galaxies of the same mass. So in redshift 1, the objects of the order of 10 to the 10 or a few times 10 to the 10, this galaxy seems to have evolved very little in terms of structure. This is what we are finding. And this is reasonable if you think twice on this, because by definition, if you bombard quite a lot of the galaxy, these galaxies, you should destroy them. So it looks like the activity of merging in these galaxies, which are relatively isolated and so on, it has been very little. Of course, I mean, if you talk with Karma, she will tell you, you have a lot of nearby galaxies that are forming the, yeah, but the contribution is really small, okay? So you have a lot of satellites here, but contributing with of the order of 100 to 500 less mass than the bulk of the total stellar halo. That's the point. So the point is, when it happened, the last large event to form something which had of the order of 4% of the stars in the outer region of the galaxy. That's the point.
being passively evolving. I mean, the same exercise you have done with the. I mean, now you are able to do that, not only for the halo, which I understand was the topic of your research, but also about the disk. So the disk is also consistent with being passively. There are many more things that have been taking place at the disk.
Look at the Milky Way, for example. The Milky Way is an example of relative passively evolving disk because it forms very little amount of stars. But today it's forming 1 solar mass per year. So that it means that it has a continuous accretion of gas and so on. So you expect the formation of a new star. But if you take a look to the Madao plot, in redshift 1 you see a quick decrease on the star formation even for the disk galaxy. So in redshift 1 to now it has decreased by a factor of 10. So for some galaxies it will look like they have been evolving passively. All the other galaxies will do more active. But in general, the full amount of galaxies, including the disk galaxies, are in the last 8 billion years has decreased the star formation quite a lot. So they are not pure passively population, but the contribution of the new star is not so huge.
I mean, it is the halo is more fossil-like than the disk. Is my point.
I understand. I think that this is right. But of course, 2 galaxies. So just I think the message that you have to take from here is that these kind of studies are now possible. This is the point.
Yeah, in that direction, since these studies are now possible, I wonder what bias you may have from the selection that you did of these 2 galaxies, and what options you have from this ultra deep field to get possibly 10, 20, 40 galaxies at this redshift and make an average, and then tell us whether these galaxies behave as the paradigm or they behave in a peculiar way.
That's a good point. So potential biases are the following. I selected the galaxies visually to appear regular. By definition, you're selecting objects that probably have been quite indeed. On the other hand, I can, let's say differently, if you take something which is an ongoing merger, you cannot make this kind of studies because you cannot separate the components. So I'm forced somehow to prove with the pilot study that the study is possible. So to your question, if you select in the Hubble Ultra Deep Field, if you select objects between 0.8 to 1.2, so around 10 to the 10. So around this, let me phrase it differently. So let's go back to the selection. So if you select objects between redshift 0.8 to 1.2, and with masses above 10 to the 10 solar masses, to select objects like the Milky Way or so on, you have, if I remember well, the details are in the paper, 15 galaxies. Of these 15, if I remember, 2 were elliptical galaxies. So I was not interested in that. I could study, but I wasn't. And the remaining, there were 4 bona fide spiral galaxies like this, and the rest were ongoing mergers or very regular ones. So I selected also those galaxies which were relative phase-on to see clearly that they were spirals and not. I could study, for example, edge-on galaxies, edge-on disk galaxies, which are just by the geometry of the universe more easy to detect edge-on than phase-on. But anyway, but if you take edge-on galaxies, the problem is that the effect of the PSS is even larger, that it has been explored in the past. The reason is the following. So if you take phase-on galaxies, the decrease of the superbrightness is relatively gentle. If you take edge-on galaxies, it decreases very quickly on the edges of the galaxy. So sharper is the profile of the galaxy, the effect of the PSF is larger. This is, you can imagine, a point source. So it's pure exponential galaxy, for example, you would be barely unable to see any effect on the outer region because of how the PSF affects. So that was one of your point. And in terms of how many galaxies we can study. Okay. And this is something that I would like to do, but limited by the amount of time and manpower, of course. So we have put 2 points here. But we are plenty of data to put points all over the redshift, between redshift 0.2, 0.3, up to redshift 1, 1.2. So there should be of the order of 30, 40 galaxies which could be studied. And in principle, this is difficult because of the three magnitudes of cosmological leaning. This should be easily accessible at redshift 0.4 or so, 0.3. So this is something that I would like to do. In fact, we have an idea that we would like to conduct now, is that we have, maybe you have heard about the SHARTS survey with the GTC, which is a survey very deep, up to 26 magnitudes in AB, in 24 different filters. Okay? So we should be able to explore the spectral energy distribution for the most closest galaxy, redshift 0.1, 0.2, and obtain and repeat this study not only with 7, 8 bands, but with 24. So that we would be in the in a very good position to explore changes not only based on color, but almost as a spectrum, and obtain age and metallicity gradients, for example. That would be fantastic also to explore. So these ideas are there. It's just a matter of people that would like to do this, or myself, but taking more time. So that's all.
Okay, so if there are no more questions, let's thank him again and